to the test. Okay, can you all see the screen? Answer yes,
Yes.
no? Okay, okay, very good. Okay, so the first question, without the zener in the circuit shown, V out is, so without the zener, so just ignore the zener diode here and just think about just this R1 and RL is going to be in series with each other. So this is represent a voltage divider then. So voltage divider, so you take V in times R load divided by R1, divided by the quantity R1 plus RL. So if you do that, the V out come to about 15 volt, okay? So the answer is D, which is none of the above. Okay, you have anybody question?
Yeah, now.
No, okay. All the yeah, the lab is yeah, definitely BYOP. Bring your own party. Okay, question number 2. With the zener in the circuit showing V out is okay. So zener. So therefore, we look at, if you look at the voltage, it goes through here. So right here would be 15 volt with just without it. So therefore, 15 volt here, causing the zener to go to breakdown. And so the voltage right here can only exist up to 5.2 volt. Okay, so therefore the zener breakdown at this point. Therefore, V out just equal to the zener voltage, which is 5.2 volt. So the answer is B, as in boy, for number 2. Okay. All right. Next one. Okay, for the circuit shown, load current IL is, oops, maybe gonna make a correction there. IL would be backspace. Okay, so for the circuit showing load IL, so IL, like we said, it's breakdown voltage, so it's going to be the 5.2 volt divided by RL. Okay, so that's why IL is equal to VZ divided by RL. So VZ is 5.2 volt divided by 1.5 kilo ohm, yield 3.47 milliamp. So the answer is B as in boy for number 3. Okay, number 4. For the circuit shown, the IR1 current is, so IR1, so they want to find the current at R1. Okay, so at R1 here. So therefore, it's going to be the voltage, the VN. So we're going to need to find the total voltage across here. So therefore, it's going to be VN minus the VZ divided by R1. That will give you the current over IR1. So that would give you 12.53 milliamp. So the answer is C as in cat for number 4. Okay. So in question? Well, everybody got it? Okay.
Yeah.
Next one. Okay, for determine the total resistance from A to B. Okay, can everyone tell me the answer to this one?
A.
There you go. Yes, A. So R1 plus R2 plus R3. It's a resistor in series, so you just add them all together. Okay, so 50 plus 1.5 kilo ohm plus 75 ohm, and that's keeping to 1625 ohm, or rounded. So if you want convert that, it's 1.625 kilo ohm. So the answer is A as an apple for number 1, for number 5. Okay, number 6, determine the total resistance from A to B. Okay. So this is look like two resistors in parallel. So what formula do we apply to this one?
Product divided by sum.
Okay, product over sum. Okay. Okay, so you take R1 times R2 divided by the quantity R1 plus R2. So that's come to 0.909 kilo ohm or equal to 909 ohm. So the answer is C as in cat for number 6. Okay, next one. You need to look at that other one. Are you okay, Kumi?
Yeah, I'm okay. Thank you.
Okay. Number 7, determine the current I1 of the circuit shown. Okay, so we need to find the current through I1 here. Okay, so this is going to be a current divider. Okay, so therefore the current divider, to find IR1, you're going to take we're going to take the total current times R2 divided by quantity R1 plus R2. Okay, so 20 milliamps times 200 ohm divided by the quantity 300 ohm plus 200 ohm, and you do that and it comes up to 8 milliamps. So the answer is B as in boy for number 7. So if IR1 is 8 milliamps, what is the value of IR2? What is I2?
It's 20 minus 8
Okay, and
is 12.
you got it. Okay. All right, number 6. Okay, resistance and current are they are inversely proportional because of resistance equals voltage divided by current. That means if the current goes up, the resistance goes down. The value of the resistance decreases. If you increase current, you have to decrease the resistance, or if you increase resistance, you have to decrease uh, the current. So that's why B as in boy for number 8. Okay, next one. Number 9, calculate the period T for the frequency of 2 kilohertz. Okay, so we got T equals 1 over F, or 1 over frequency, which equal to 1 over 2 kilohertz, which yields 0.5 millisecond. Okay, so the answer is A look like 5 microsecond, B is 0.5 microsecond, and C is 0.5 millisecond. So the answer is C as in cat for number 9. Okay. Okay, number 10, a sine wave with a peak-to-peak value of 10 volt has a VRMS value of, okay, so we want to do is, so this is 10 volt, and that's, they said it's peak-to-peak, okay? So we want to do is find out what the peak value, so take the 10 divided by 2, that'll give you the peak value, and you take the peak value, multiply that by 707, that give you a 3.535 volt VRMS. Okay, so the answer is B as in boy for number 10. Okay, you're good?
Yeah.
Okay, next one. Okay, determine the voltage V out for the circuit shown. Okay, so we got, so V out is going to be way out here. So therefore we're going to be look at the total. So V out is going to be taking the voltage that goes in here. Okay, and then it's going to take into consideration of, so you're going to times R, let's see, it's going to take times R2 here. Okay, so this one is going through here. So this one is the same thing. Okay, so this one is not connected to anything. And so therefore, this is sort of like an open circuit. Okay, so an open circuit kind of ignore over going to R3. So therefore, you only look at just this point right here. Okay, so R1 and R2 is going to be in series. Okay, and then we come back into that voltage divider. So there's R1 and R2. So that's why we take the E, the voltage, times R2 divided by the total resistance, so R1 plus R2. So that's why, and that would give you a 24 volt. So VB or VB right here would be 24 volt. And that also would be the same thing as V out. Okay. Yeah, if this one is connected to the common, then then it would be different. But this one is, it's just an open. It's not connected to anything. So VB and V out would be the same value.
It's kind of a roundabout way to do it, but you could also add the two resistors up and get the current. And then once you get the current, since it's in series, multiply it times the resistor at each one, and you'd have a voltage drop across each one.
Right, but and then
I'm
it
no,
was
I'm no, I agree with you, Sam. I'm just saying if
Okay.
that's a roundabout way, but you could find it that way as well.
right. Okay. So that's so B as in boy for number 11. Number 12, find IR1. So IR1 would be here. Like I said, VB would be like 24 volt, and you got this side, so the 2 voltage. So the E1 minus V out or at VB divided by R1. So therefore, it's going to be 40 volt minus the 24 volt divided by 50 ohm. And that's give you 0.32 amp. So the answer is A as in apple for number 12. Okay. Next one. Okay, 13 for the circuit for the circuit below. Solve for V out. Okay. So V out is going to be here. So V out is going to be just the voltage that drop over this diode right here. What is the voltage drop for diode?
0.7 volts.
0.7 volt, correct. Okay, so the answer is B as in boy for number 13. Okay. Just over this diode, this simple diode right here. So V out is going to be measured from here to ground. So it's going to be 0.7. So that's the answer B for boy for number 13. Number 14 for the circuit below. Solve for the current I. Okay, so I. So we want to do is take the current. So we know that 0.7 is here, and we know that 10 volt is here. So 10 minus the 0.7. That would be 9.3 volt divided by 1 kilo ohm. That would be 9.3 milliamp. So the answer is C as in cat for number 14. Okay, next one. Okay, for the 15 for the circuit below, solve for V out. Okay, so V out, like I said, so V out is here. So V out, when you're going to go this way, this is going to be causing this one to be, so the voltage here is going to be higher than the voltage here. So this one is going to be an open. Okay, so an open is like it's almost like cutting the diode out the circuit. So therefore, whatever the voltage comes in also exists at the V out. So that's why V out equal to just the V bias of the circuit, which is 5 volt. So the answer is A as an apple for number 15. For 16, for the below circuit, solve for the current I through R limit. Okay, so I equal to V bias minus the V out divided by R limit. Okay, so 5 volt minus the 5 volt would be, that would be 0 divided by 1 kilo ohm would be 0 milliamp. So zero, there's no current. Okay, so the answer is A as an apple for number 16. Okay, any question? All right, next one. Okay, so this one okay. When the diode is forward biased and the bias voltage is increased, the voltage across the diode, assuming practical model, will, okay. So when it's forward bias, so therefore, when that happens, there's nothing going to, that's going to be, yeah, once that is going to be turned on, and it's going to be, there's nothing to, It will not change that voltage. Okay. Yeah, the diode over the diode, it's just 0.7. So there's nothing's going to change it. It's going to still 0.7. Okay, so the answer is C as in cat for 17. Number 18, when forward bias, a diode, okay. So when it's forward bias, it conduct. So therefore, the answer is B as in conduct current. B as in boy for number 18. All right, 19 for the circuit shown, the VP out is, so we want to find the voltage peak out, okay? In this case, it's going through here, so voltage, so this one is voltage peak, and so from here to here is 5 volt, from here to here is 5 volt. So peak to peak would be 10 volt, but we need just 5 volt, so VN would be going through here, so 5 minus the minus this diode, 0.7. Give you a 4.3 volt peak. Okay, so the answer is A for 4.3 volt. A as an apple for number 19. Okay, for 20 for the circuit showing, the VRMS or the V out is, okay, so V out is equal to the 0.707 times the V peak out. So V peak out was 4.3, so 0.707 times 4.3 volt peak equal 3.04 VRMS. So the answer is A as an apple for number 20.
Wait, no, the answer I think is B.
Yeah, the answer is B. Sorry, I put it in the wrong place. Thank you, Richard.
Sam, can you go back to number 17 and 18? Explain the difference between those two for me, please.
17, okay, when a diode is forward bias and the bias voltage is increased, the voltage across the diode, assuming, okay, so just think about, let me see if we have a picture of transistor here somewhere. Look like I don't think I have any picture of transistor on here, but it's.
That's just saying that no matter what the input voltage is, the forward voltage drop across the diode will always be 0.7, right?
Yeah, then over a diode, it's going to stay at 0.7, no matter how much it's almost the voltage that you put in, the VCC, right? You can put in 10, 20 volt, 30 volt, 50 volt, doesn't matter. The voltage over the diode, the little diode to bias, it's still a 0.7. So it doesn't change. Yeah, it doesn't change it at all. Okay.
But how come the answer is different? Conducting current and, okay.
For 17, no, current is different. When you're talking about the voltage to bias to make sure the transistor work is that the gate has to be more positive than the emitter. Oh, the gate has that had to be, the base had to be more positive than the emitter. Okay, so therefore remember it's just 0.7. The diode had to be, it's always going to exist. They wanted to find the voltage across the diode. So over across the diode, it's still 0.7 no matter what, unless you use a different type of diode, which is, then it would be that value. Okay.
All right,
but it doesn't change. Yeah, it doesn't change as it. But the current would be different because you can bias, and so you can open up the path where the current can flow. Okay, when it's forward bias, the current can flow through. Okay.
Okay, yeah, I didn't pay attention to that current.
Okay.
Thank you.
Maybe if another way of looking at that is that the diode current increases exponentially with a very small increase in voltage.
Yes.
So no matter how much current you're flowing through the diode, the voltage changes very, very little. And for the practical model, for just a simplified model, we just assume it stays at 0.7, although it increases a little as the current increases. It decreases just a little as the current decreases.
Yes,
but the best approximation is 0.7 volts.
Correct. Thank you.
Thanks, Richard.
Okay, so 19, everyone's good. 19, the answer is A for apple, and number 20 was B as in Bob. Okay, so number 21. Okay, for the circuit shown, the peak secondary voltage is, okay, so we're going to be putting in 156 voltage peak to peak, look like from here to here. So therefore, if we look at just the peak wise, that's going to take the peak to peak divided by 2. Okay, so divided by 2. So therefore, it's going to be this one look like 156 here and then 156 going down. So that is going here. And so we want to do multiply against the turn ratio. So it's going to be 156 volt peak times the 1/2. So that's 78 volt. So it's a step down transformer. So you have 156 on this side and 78 would be on this side. Okay. So the answer is C as in cat for number 21. 22 for the circuit shown, the rectifier output voltage is, okay, so if we got 78 here, it need to go to, so it go through this rectifier, so it go through the diode, so 78 minus the 0.7 volt over the diode, give you 77.3 volt peak, okay? So the answer is A as an apple for number 22. Okay, everyone's good? Any question? All right, next one. Okay, 23 for circuit shown, the peak V out voltage is, okay, so we want a V out, so V out will be over here, okay? So we're gonna be so 100 volt here, 100 volt here, so we're gonna be 100 volt, so from here to here, so this is 2 to 1, so 100 on this side, it's gonna be 50 on the other side, okay? So on the secondary, it'd be 50, and then this 50 is going to be a center tap, okay? A center tap, so therefore 25 exists on this side, 25 would exist on this side. So 25 minus the diode D1 will be going out to the V out, okay? So 25 minus the 0.7 volt, it got 24.3 volt, okay? So V out will be 24.3 volt. So the answer is B as in Bob for number 23. Okay, so well, let me see. Okay, for 24, the frequency of Vn is 10 kilohertz. What is the V out frequency? Okay, so this is so this one is a so we got a so this one is going to be a one phase. So this one is going to be here, and then we're going to go through here. It's going to get double. So this is going to be this side, and this side is going to be the other side. So it's going to be double the frequency from the input. Okay, so it's going to be so 10 here and then going to be 20 out. Okay, so the answer is C as in cat for number 24. All right, next one. Okay, number 25 for the circuit shown, the secondary peak voltage is, so we're going to be secondary here. Okay, so we got 110 VRMS, which is coming down here. So it's going to be on this side, it's going to be a step down again. It's going to step down by 5. So 110 divided by 5. Okay, that's give you about 22 VRMS. Okay, but the answer they wanted was in peak. So we have to convert that 22 VRMS to peak by taking the 22 divided by 0.707, that give you 31.12 volt peak. Okay, so the answer is C as in cat for number 25. Okay. All right, so number 26. This for the circuit showing, calculate V peak output out. Okay, so VP out. So VP out, V peak out equal to V secondary minus the 2 diode that is turned on. So there'll be 31.12 VP minus the 2 times 0.7 volt. That give you 29.72 volt peak. Okay, so the answer is A as an apple for 26. Okay, any question? Okay. Okay, next one. Okay, 27 for the circuit showing, calculate V out. Okay, so V out equal to, okay, so we're doing the same thing as this one here. So we do just go through the whole circuit. We just want to take this one into, just look at the two resistor first and then figure out what the voltage would be between the two resistor. Okay, so this way you look, if you multiply this one against this one, it would come in somewhere in around maybe close to about 18 volt. So therefore this is going to go into a breakdown. So therefore it's going to be, the voltage out is only 5.1 volt. Okay. So here the Zener diode is going to go break down again. And so V out is just 5.1. That's the maximum that voltage will go. Okay, so the answer is A as in apple for 27. Okay, for 28, for the circuit showing, calculate total current IT. Okay, so IT is going to be here. Same thing what we said, Vn minus the Vz divided by R1. Okay, so Vn was 24 minus the 5.1 volt divided by 1.2 kilo ohm. Okay, that's give you 15.75 milliamps. So the answer is C as in cat for number 28. Okay, all right, next one. Okay, for the circuit showing, calculate load current IL. Okay, so IL would be over here. So we're going to be calculating that. So IL, so we're going to be, so the voltage, like I said, it's going to be just the VZ, that's going to be here. Okay, VZ minus the common would be 0. So therefore it's going to be 5.1 volt divided by RL, which is 1.8 kilo ohm. So the answer is come to 2.83 milliamps. So the answer is B as in boy for number 29. Okay, for the circuit, for number 30, for the circuit showing, calculate Zener current IZ. Okay, so IZ would be here. Okay, so current IZ. So therefore, first thing you want to do is, we know that if we look at the total current minus the current that's going to the IL, that give you the that will give you the total, the IZ. Okay, so what was the I total? I total was the 15.75 from number 28, and minus the IL, the 2.83, so that gives you 12.92 milliamp. So the answer is A as in apple for number 30. Okay, any question? All right, next one. Okay, number 31 for the circuit show, and calculate V out. Okay, so we're going to be doing the same thing as like we said before. We just kind of ignore this the VZ for now and just focus on just looking at the two resistors, the R1 and RL. Okay, so we do that calculation. So we'll do that okay. So we do this calculation. So if we look at this one, it's going to be open. Okay, so they're going to be 24 times the 5K divided by the quantity R1 plus R2, RL, so 10 plus 5K. That's give you 8 volt. Okay, so the answer is A as in apple for number 31. Okay, so 32 for the circuit showing, calculate the Zener current IZ. Okay, so we want to look at this one. The Zener diode is open because we put in the 24 volt. So 24 volt that goes here. What was the voltage V out here was 8 volt. Okay, 8 volt. So therefore, it's not into it's not in breakdown or anything. So therefore, so you got 8 volt here, and so therefore this one is going to be just operate like a normal diode. And since 8 volt is higher on this side, so therefore this Zener become an open, because 8 volt is less than It's less than the breakdown. So therefore, this one, you think about the normal diode, okay? So you got a 0 volt on the anode and you got the cathode, it's gonna be 8 volt. So therefore, this one is reverse bias. So therefore, this one would be an open. And so just kind of ignore the Zener diode, okay? So therefore, it's gonna be an open, cause an open circuit. So IZ would be 0, okay? There's nothing, because once this is open, there's no current travel through it, okay? All right, so the answer is C as in cat for 32. Okay, next one. For operation as an amplifier, the base of an NPN transistor must be, okay. So in order for an amplifier, it must be in forward bias. So in forward bias, the base has to be more positive with respect to the emitter, okay? So the answer is A as in apple, for 33. Okay, 34, the emitter current is always, okay? So the answer is, it's always, remember, so it's greater, the emitter is like the total current that's coming from the base as well as it's coming from the collector. So it's like the total also. So it's going to be always much greater than the base, and it's going to be always be greater than the collector. So the answer is D, as in David, for number 34. Okay. 35, so the beta DC of a transistor is, okay, so remember we got beta equals to IC divided by IB, okay? IC over IB, so therefore it's a current gain. Okay. So the answer is A as an apple for 35. Any question? Okay. 36. When operating cutoff and saturation, the transistor acts like a, okay, yeah, we're going to turn on and off. That's all it's going to be turned, either in the 0 voltage or it's going to be on the high voltage, either logic 0 or logic 1. Okay, it just operates just like switch. It's just on and off. Okay, so the answer is B for number 36. Okay, 37, in saturation, VCE is, okay, VCE is going to be very, very, very small, okay? So it's a minimum amount. So the answer is C as in cat for number 37. Okay, 38, if the base emitter junction is open, the collector voltage is, okay, so if the base to the emitter is open, so the collector must equal to the voltage that you put in, the bias voltage, which is VCC. Okay, so the answer is A as an apple for number 38. Any question? Okay. All right, 39. For the circuit shown, calculate VB, okay? VB is the same thing, like we said, it's going to be a voltage divider because R1 and R2 is in series with each other. So it's going to take the voltage of VCC times R2 divided by the quantity of R1 plus R2. Okay, so that gives you a 7.5 volt at the base. So the answer is B as in boy for number 39. Okay. Number 40, for the circuit shown, calculate the emitter's current IE. Okay, so IE is equal to VE divided by RE. Okay, so VE is VB minus the 0.707 for the diode and divided by RE, which is 2.2 kilo ohm. Okay, so therefore the answer is come to 3.09 milliamps. Okay, so the answer is C as in cat for number 40. 41, for the circuit shown. Okay, let me see. Okay, for the circuit shown, calculate the base current IB. Okay, IB is equal to IE divided by the quantity 1 plus beta DC. Okay, equal to, so we got IB was the IB, we got IE, which is 3.09 milliamps divided by 1 plus 150 for beta. Okay, so the answer comes to 0.0205 milliamp. So the answer is A as in apple for 41. Okay. Any question? All right. All right, 40. A certain common emitters amplifier has a voltage gain of 100. If the emitter bypass capacitor is removed, what happened? Okay. What happened to the voltage?
It's decreased.
You're gonna, yeah, you decrease because there's no bypass, because of some of the voltage is going to be feeding back into the input, and so therefore there's more input now. So therefore you're going to subtract. If you take the V out divided by the V in, it's going to be a smaller voltage gain. Okay, so the answer is B, as in boy, for number 42. Okay, 43. The input resistance of a common base amplifier is. Okay, so this one is a common base. It usually is very, very low. So the answer is A as in apple for 43. Okay, in the differential mode. Okay, in differential mode, usually you apply two voltage. One is positive and one is negative, and they will end up canceling each other out. So the answer is A as opposite polarity signal applied to the input. So because we want to compare, make sure that they don't want, if it's beyond that, then it goes into saturation. We don't want that into saturation. We want it's within that time, in that. So we want one positive, one negative. Okay, so A as an apple and for 44. Okay, number 5, in a common emitter transistor circuit, the AC input signal is applied between the. Okay, common emitter. So emitter is connected to the ground. So where do you put in your input? Okay, so you only have two, either base or the collector. Usually collector is the output, so the input has to come in through the base. Okay, so the base and emitter. Since emitter is connected to common, so therefore the base and the emitter. Okay, so the answer is D as in David for number 45. 46, in a CE transistor circuit, the AC output signal is taken between the, we just said a minute ago, so the collector is going to be the output. Okay, so collector and the ground, it would be the output. So the answer is B as in Bob for 46. Okay, any question?
No.
All right, 47. The coupling capacitor in RC couple amplifier. Okay, what when you couple in a capacitor, what is the purpose of that capacitor? Mrs. Smith, you got this one.
You're in charge, man.
No, you know this one. What does the capacitor do?
What does the capacitor do? It passes AC and block DC.
Okay, very good. Okay, so the answer is B as in boy, 7. All right. So 48, determine V out the circuit shown. Okay. So in this circuit, so we're going to be, this one is going to be, so the total of the voltage input says here you got 1K and 1K, and you got the RF, the feedback resistor. And so this is applied to the to inverting side. So therefore it's going to be negative RF divided by the Rin. So Rin is going to be 1 and 10. So your gain is negative 10. So negative 10 times your total of this, the input here. So 0.2 volt plus 0.7 volt, that's going to be 0.7 volt. So 0.7 volt times negative 10 would be given negative 7 volt. Okay.
I
So
think
the,
Wasn't that the one that was in the handout? And I also Ty, I think he did that. It's like a summing type thing, right?
Yeah, well, pretty close. Yeah, exactly. Because you're going to be just looking at this, and since you have the same input resistance and your same input
The
feedback
one that Ty
resistance.
used and the one that was in the handout, I think it used 3 resistors, but it went like minus, and then it had quantity V1 plus V2 plus V3 like
Yes.
that. So
So
so if you could remember that, then you just plug in
yeah,
the
you just
value.
add the input and then multiply against the gain.
That only works if the input resistors are the same for each input channel.
Yes,
Yeah, okay.
you got it. Thank you, Richard. Okay, so the answer is B as in boy, -7 volt for 48. Okay, any question? All right, and next one. Okay, so and this one's a bandpass filter generate maximum gain. Okay, so maximum gain is at the center frequency and within its pass band. So you got upper frequency, lower frequency, upper frequency. So within its pass band, that's where you get the maximum gain. Okay, so that's when you hear the signals very, very clear. Okay. So that's it. So the answer is D as in David for number 49. Number 50, the response of a bandpass filter is characterized by its center frequency and its -3 dB, okay, which is at the lower cutoff. So, so that, and the answer is D as in David for number 50. Okay, any question? All right. 51, for the circuit shown, solve for IDQ, okay? So in this one, IDQ, so IDQ would be the same thing as, so ID at the drain. It's the same thing as similar to the current that is going through the, okay, going through, okay, gate, and then source, okay, going through the source. Okay, so therefore it's going to be, so IDQ is equal to IS, which equal VS divided by RS. We know that VS is 2 volt divided by RS, 240 ohm. That's give you 0.0083 milliamps or 8.3 microamp. Hold on, let me see. No, that's V amp. Okay, this is what's amp, so this is milliamp. Sorry about my, so this is milli, so this is going to be just amp, delete, okay. So this one is divided by that will be amp, and it will be 8.3 milliamp. So the answer is A as an apple for 51. Okay, 52 for the circuit shown, solve for VGS. Okay, VGS equal VG minus VS. VG is going to be 0 volt minus the VS, the 2 volt. That's give you -2 volt. So the answer is A as an apple for 52. Okay, any question? All right. Number 53 for the circuit shown, solve for transconductant, okay, GMO, okay, GM0, okay, so GM0 equals 2 times IDSS divided by the absolute value of VGS off, okay, so 2 times 15 milliamps divided by absolute value of -8 volt. So that's come to 3.75 millisiemens. So the answer is A as an apple for number 53. Okay, and then 54, you're going to use the GM0. Okay, so GM is equal to GM0 times the quantity 1 minus VGS divided by VGS off. Okay, so you got a 3.75 millisiemens times the quantity 1 minus -2 volt divided by -8 volt. So that total together comes into 2.8125 millisiemens. Okay, so in this case, we don't, it's not A, it's not B, it's not C. So the answer is D, none of the above. Okay. Any question? No? Okay. All right, next one. Okay, for the N channel D MOSFET with a positive VGS is operating in. Okay, if it's positive, it's going to be enhancement mode. And when it's negative, it's in depletion mode. Okay, so this is operating in the positive, so therefore it's in enhancement mode. So B as in Bob for number 55. Number 56, determine the VS for the circuit shown. Okay, VS equals IDQ times RS. Okay, so IDQ is was 2.7 milliamps times 2.4 kilo ohm. It could yield 6.48 volt. Okay, so IDQ was from previous step. IDQ, no, not from the IDQ was.
At what they given.
Is on the red. Is on the red.
Okay, thank you. Okay, so IDQ, IT 2.7. Okay, yes. Okay, so the okay, so the answer is C as in cat for number 56. Okay, next one. 57. Determine the VGS for the circuit shown. Okay, so we know that. Okay, so we're gonna be VGS equal VG minus VS. VG is going to be 0 volt minus the IS with same thing, IDQ times RS. So IDQ is 2.7 milliamps times RS, which is 2.4 kilo ohm. That yield negative 6.48 volt. So the answer is B as in Bob for number 57. Okay. Okay, 58, determine the VD for the circuit shown. Okay, so VD equal VDD minus VD. So for VDD is going to be 20 volt minus the IDQ times RD. So 20 volt minus 2.7 milliamps times 6.2 kilo ohm. That will give you the answer is 3.26 volt. So the answer is A as an apple for number 58. Okay, any question? No? Okay, next one. Okay, determine the gain AV of the circuit shown. Okay, so this is a non-inverting because the input is applied to the positive side of the amplifier. So the gain is going to be 1 plus the RF divided by Rin. So therefore, it's going 1 plus RF would be 100 kilo ohm divided by 4.7 kilo ohm. So the gain would be 22.28. Okay, and then we're going, there's no unit for that. So the answer is C as in cat for number 59. Okay, number 6, and we want to find the IRI. So therefore, it's going to be the VN times R divided by RI. So VN that goes here, it also exists here. So therefore, it also exists right here. So VN is going to be 4.5 minus this divided by this resistant. So the answer is 0.957 milliamp. So the answer is B as in Bob for number 60. Okay, any question? You follow, Kumi?
Yeah.
Okay.
Just confused.
Which part are you confused?
No, I got it now. Thank you.
Okay, yeah, just make sure it's clear. Okay.
Yes.
Okay, the bandwidth of a DC amplifier having upper critical frequency of 100 kilohertz is, okay, so it's going to be just 100 kilohertz. So you got the upper frequency going to be 100 and the lower would be at zero hertz. So it would be 100 kilohertz minus 0 hertz would be just give you 100 kilohertz. So the answer is A as in apple for number 61. Okay, 62. The bandwidth of an AC amplifier having a lower cutoff, lower critical frequency of 1 kilohertz and an upper critical frequency of 10 kilohertz is. So that's bandwidth equals upper frequency minus the lower frequency. So therefore 10 kilohertz minus 1 kilohertz would equal to 9 kilohertz. So the answer is B as in Bob for number 62.
Sam,
Yes.
number 61, they say the bandwidth of a DC amplifier for upper critical frequency of 100, but it doesn't tell you what the lower frequency is.
Yeah, if it doesn't mention, we always measure something from the zero frequency.
So you
So
just
so
assume-
if they tell you the upper side, then the bottom side has to be at zero. Yeah, because we don't do negative frequency.
The clue there is in the question, a DC amplifier. So that means if it amplifies DC, the lower frequency is 0.
Yeah,
Okay.
because of DC, there's no frequency.
Okay. All right. Thank you.
You're welcome. Okay, so number 63, determine the current I in of the circuit shown. Okay, so I in, so it's going to be right here. So it's going to be this one, this voltage at V in minus the voltage here, which is this one is a virtual ground, which would be 0. So therefore, we just take the V in divided by the R in. So the 4.2 volt divided by 2.2 kilo ohm, it give you a 1.91 milliamp. So the answer is B as in Bob for number 63. Okay. Any question? If you do, Richard can answer this question. Okay, no question. All right, determine the gain AV of the circuit shown. Okay, so in this one is an inverting amplifier. So it's going to be the gain equals negative RF divided by RN. So 22 kilo, negative 22 kilo ohm divided by 2.2 kilo ohm would equal to negative 10. So gain is negative 10. So the answer is A as in apple for 64. 65, determine the V out the circuit shown. Okay, so V out equal to the gain times the input voltage. So it can be negative 10 times the 1 volt that's coming in. So the answer is negative 10 volt going out. So the answer is C as in cat for number 65. Okay, any question? Look like you have a question, Kumi?
A lot.
Okay, well, go ahead and ask. Please ask and make sure you understand.
That's a whole class.
No, please ask because you know if you don't understand, you have to ask it so we can go through it. And which part do you not understand?
61 and 62, we can do the same formula.
Okay, 61, 62, yes. Because like Richard said, when we look at the DC doesn't have any frequency. So the low frequency is going to be 0 volt, 0. So the lower side, the low frequency is going to be 0. And the upper part is 100.
Always.
Right? Yeah, and this when you just said DC, it means the low, DC doesn't have any frequency. So therefore it's going to be 0 hertz at the lower side, and the upper side is going to be 100 kilohertz. So 100 kilohertz, so the upper is going to be 100 minus the 0 hertz. It gives you just 100 kilohertz, which is A for number 61. And then and you understand 62, right? Because they give you the upper and the lower.
Yeah, this one I understand, the 62.
Okay.
Okay, thank you.
Okay, you're welcome.
Another way of understanding a DC amplifier is to refer to it as a low pass amplifier.
There you go.
Thank you.
Okay, you're welcome. Okay. All right, so we're at 60, 64 and 65, you good?
Yeah.
All right. Okay, 66. Okay, well, 33 dBm equal to how many, what's the output? They want to know that in watt So therefore, P out equal P in times 10 raised to the power dBm divided by 10. So we got P in is going to dBm, reference to P in is 1 milliwatt times 10 raised to the quantity 33 divided by 10. So you multiply that and you should get to 1.995 watt. You can round it off to 2 watt. So the answer is C as in cat for number 66. Okay, 67. An amplifier has an output of 25 watt expressed in dBW. Okay, so dBW equal 10 times log of the quantity P out divided by P in. So 10 times log 25 watt divided by 1 watt. So in other words, 10 times log of 25. And the answers come to 13.98 dBW. So 67, it's going to be B as in boy. Okay. Okay. You're good. All right. Next one, last two. Okay. For the second showing, the out, okay, the out equals, okay, so for the second showing, so we're going to find the out. So out is here. So out is going here. So 2 is going in. So 2 plus the 10, that's going to be 12. And then minus the 3, that would be 9. Plus the 10, that would be 19. Minus the 3, that would be 17. So 9 minus 3,
16.
16. 16, and then plus the 10 will be 26. So that 26 will go out. So 26 dBm. So the answer is B as in Bob for number 68. You follow, Kumi?
Can you say that one more time?
Okay, so you can be, okay, just follow this circuit. Okay, so attenuator is represent something that gets reduced in sound, okay? So when you got amplifier, so therefore you can be a 2 plus the 10 first amplifier, and then after that it get attenuated, so drop by 3, and then you get an amplifier again, 10, and then you're going to be minus the 3 dB, the attenuator, and then you get, and then you plus the 10 of the amplifier at the end, okay? And so if you go through, positive 2 plus 10 minus 3 plus 10 minus 3 plus 10 would equal to 26. Remember the other one that we did before, this one was a plus 3 from the homework, remember? The input was positive 3, so therefore the answer was 27 dBm at the end. So this one is going to be 26, which is 1 less. So the answer is B as in Bob for number 68.
He
Okay.
deliberately tried to trick you.
And so yeah, we tried to get, especially you tried to get Mr. Smith to get this one to be incorrect. Okay. 69, 2 stages has decibel power gain of 20 and 5. The total ordinary power gain is, so therefore AP, the ordinary gain equal to 10 raised to the quantity dB divided by 10. Okay, so 10, okay, so dB is going to be 20 and 5, so 20, so 10 plus 5, 20 plus 5, 25 divided by 10. So therefore, okay, so that could be 2.5. So 10 raised to 2.5, the answer is come to 3.16. 3.16.2. Okay. So the answer is C as in cat for number 69.
Bingo, bingo.
Where did you get 5?
5 right here, say 5.
Oh,
20 and 5.
oh,
So total to get both of them is 25. So 20 plus the 5 be 25. Divided by 10, that would be 2.5. So 10 raised to 2.5. So if you put that in your calculator, it should be 3.16.
Bingo.
Thank
Okay,
you.
bingo. Don't we have a don't we have to change 2 dBm to dB? No, in this case you don't have to because you have only 1 dBm. dBm can add to any value of dB, but it can if it add to dBm plus a dBm, then we have to convert it to ordinary gain first. But in this case, no, you don't need to. You just add it together. The answer at the end you take it in the form of dBm. Okay, because we only have 1 dBm.
Another way of looking at it is if you look at just the amplifier attenuator chain, the total gain is 30 minus 6 or
30.
32
10, 10,
20
10.
30 minus 6,
That's it.
24 dBm. So,
Yes.
I mean, 24 dB.
Yes.
So whatever input you have, you just add 24 to it and
Yes.
to get the output,
You got
whether
it.
it's 2 dBm or 3 dBm or 10 dBm.
Okay.
The
Very
gain
good.
of the amplifier chain is 26 dB.
Yes. So you got this 10 plus 10 plus 10. So that's 30. Okay. And then minus the 3 and so minus the 6, which is the attenuator. So that's what Richard was talking about. So minus 6. So the total would be 24 here in the chain in the amplifier. And then plus the input, which is the 2. So the output would be 26.
Yes, I do that way. But
Okay,
the way
good.
you do it, that's why I'm more good.
Thank you, Richard.
Thank
Okay,
you.
see, now we
You're
can have a
welcome.
team together. Okay, so anybody have any question?
I have a comment, I think.
Yes, yes, Richard.
This test was hard.
Yeah.
And especially given the time limit. So, and I mean, anyone who, you know, fell short of perfection should not feel bad about this. I mean, when it got to the MOSFET ones where you had to remember earlier answers,
Yes,
I got messed up. I missed some of those. So,
yes,
you know, it was hard.
right.
Richard, I can't imagine you getting messed up.
I missed 2.
Yeah. So like I said,
Richard,
yeah,
you're my hero, man. I can't imagine you getting messed up.
yeah, it's almost like, you know, they want to, you know, sort of prepare you, say that if you go to a company, they give you a certain amount of time to do the testing. And then after that, they just look at the end result. You know, you don't get any more time than that. And so,
I
This
come
is-
back to see Mr. Pham.
yeah, well, maybe next time we'll put more time onto it, but that was the 2 minute per. So yeah, time was pretty quick on this one. Okay,
Mike.
so that's pretty much it. So back to you, Mr. Pham. Thank you.
Okay, thank you very much, Sam.
You're
Thank
welcome.
you.
You're doing very good job.
Thank you.
Okay, now, this is like very, very basic. That means when you're looking into that, you know right away what to do. Not looking any information. The thing in interview, you don't have anything with you.
I bring my notepad.
Not
No,
allowed.
don't take your notepad. Bring series with you.
Even the cell phone, nothing at all.
Oh.
Okay, the thing is when they want to hire you to be a technician, then they given you the first will be the test. If you get over 90, then they can be set up for your interview. Otherwise, they can say thank you. That's why I try to prepare for the final. That means when you get the interview, that only thing you need to go over and over and over. Otherwise, too many things in the program, you cannot look into which one. Okay? And that's a very, very basic. And my question is it a 2 minutes, it's a short, or we need more time?
More time, please.
Okay.
Yeah, like Richard said, when you're doing the transconductant, because that requires a little bit more time to think through, because that one, the formula, they haven't had a chance to work with that too
Okay.
often.
That's what I want to know. The thing is, next semester on the AC, you're doing the same thing. You will be get the quiz. Okay? And guarantee you really understand it. And that's what I base on to see the student really learning or understanding. You see, in the program, we get too many students apply for. However, to the end, how many people able to get through it? The reason we allow anyone to get into the program is a city requirement. One class must be at least 25 students. If less than that, then they cancel. So that's why this time I also have to do, I have to see how many people want to register now. I have to do it so I can report it. They already warning me they can cancel one class. But okay, we get it enough students for this summer. So we don't have any problem. But that is the way they're not doing the right way for technical training. But what can I do? I teaching for the college or university must be better. The thing that they want to learn, then they have to learn it. Otherwise, they can drop and doesn't matter to me. I have to handle this situation for over 35 years. Okay, so any more questions or anything else? I can.
So just like the two students did, Mr. Pham, you said they can't take their cell phones, but they showed these two students taking a test. One was in the test room and the other one was outside, and they were talking back and forth on their cell phone. So you can't do that, huh?
Right, that's what the thing is, you can store too many things in your cell phone.
Mm-hmm. So
And
you can call Sam. You're in the classroom doing the test and call Sam outside the classroom, and then he can relay you the answers.
Yeah, that's why some students, they get a hard time. However, some other one, the interview, they get take two level, two right away. That means they get paid more than $25 an hour.
Yeah, I went to one of those exams one time, and they required that you leave your cell phone, pens, pencils, purse, wallet, everything in the trunk of your car. They don't want you to bring it in.
You can't do that.
Yeah, yes, they do.
I need my phone.
And before they hiring you, and they send a letter into the school, normally to me.
Wow.
To say what I telling them about the student. So that's why in the program, some people I already know. The thing is they're active. They're doing very good. But some people I never know. What can I do?
So the moral of this tale is be nice to Mr. Pham.
Right.
Yeah, the thing is, in the program, I know who can do, who cannot do. They've been with me almost a year.
Hey, Mr. Pham, when you do the Tech 1, the summer class, now is Tech 1 and Tech 2 are going to do the AC theory, correct?
Exactly.
Okay.
Only thing is the first week, I need the time to teach the new student on the basic DC circuitry. Only 2 days, that's good enough to cover everything on the DC. Nothing, really important thing. Just a very basic to understand how the current flowing, what the voltage, or calculate the power, something very basic.
Yeah, so what I was gonna say then, you just gonna have the old students sit in because they gotta log on, but don't really like get involved because you'll be teaching the new students.
Yeah, that means I like, the students still in the program no matter which day. The thing is that's just a review. Sometimes you have to understand you learning one time. You cannot understand exactly.
Mhm.
Have to be few times. That's why I told them in order to learn it, then you must be reading over and over. The first time the lecture you reading you not quite understand. Second time get better and more time. Then now you really understand it. That's what my period when I went to the university. But the thing in here, we try to take it what? When I really care about doing the lab, when you're doing the lab, if you don't know what to do, don't do it. Have to ask it. Otherwise, will be damage to the circuit board, damage to the system. And that's a big problem. And that's why we try to help them how to isolate the problem. Is it you not build the circuit right, or the oscilloscope not working, or the scope probe is not working, or generator not working? That means too many unknown. Then we need to know how to isolate it one by one. I've been doing my job for 25 years, just deal with that kind of problem. Something wrong, what can we do? That's what technicians have to do at work. Circuit board not working, they give it to you, fix it. If you don't know how to do what to do, sooner or later when they get laid off, you go. Okay, any more questions, anything else?
So, Mr. Pham, if we have any questions over the weekend, just text message you first, correct?
Correctly, doesn't, I'm still working anyway. But this time I don't have much time to prepare for the next week and for the following week. The thing is, this week we have to working on the report, the student, okay, for the grade, for the hour, everything, and have to be must be done before Sunday.
Okay.
A lot of work. And when we going back to the class, they not look like we're doing right now. That means at that time we get only take one class only. And only one class for tech tube. Not like this time they try to doing exactly the ESL class. They given one instructor for one CIN number. We cannot follow it. The thing is what happened. In this program, I have to monitor the student. First thing is the process they doing in the program. Second thing, how many hours they get on the first semester, and then when go to the second semester, we have to carry over. Okay? So when we already set it up, everything, now one student try to get into the program. So we have to make tell by alphabet. So I have to adding into the middle of the list. That give me a hard time. Okay, so basically from the 4, we get only one take 1 CIN number, one class, one for take 2. Everyone will be go into the same CIN number for take 1 or take 2. Not I divide it like we're doing right now. If they want this way, I say, okay, you guys go with. I'm not running anymore. Take too much time. And didn't make sense. The thing is, Mid City, they run more class will be ESL class. ESL class after one semester, they don't care anything. They don't care about the hour recorded to carry to the next one. So that's more easy for them. But in this program, I running the program. I get the instructor doing the assistant for me. That means they cannot do what they want. I just telling who doing what. And one lab instructor have to do for take 1 and take 2. Not only take 1. Okay? And also, internet not working. We have to fix it. Computer down. We have to fix it. Circuitry in the lab, they not working. We have to fix it. Also, the system level is not good. We have to do everything. So that's why in the program, one instructor have to take care of that. Like, one level system going down, then I have to say, you try to fix it to make it running up tomorrow. Then they have to do it what? No matter, I don't care. They can spend the time to fix the problem, and next day, if they don't want it, they can stay home. They don't have to teach. You compensate for the hour. That is the way program be running. No one can run only single class. And if I'm not teaching, I guarantee all of the instructor will be not working, not teaching at all. The thing is, nobody can do. City pay just a part-time, just a few hours a day. We own engineering. You working for the engineering job, you can get paid for over 80K up to 100K a year. And now you're working on this program, how much? You get 30K a year. If you're just doing like they give pay for you, then the program cannot run. Not enough time for you to teach, to prepare, to do everything. City cannot help the program to fix anything. They don't have it. People to do it. And they don't know what to do either. We own engineering. Okay? So we can do whatever the other people can do. So I hope you can understand the situation in the program that are very, very hard. The reason we can do it, the thing is, I'm already retired. Everything. I don't need to working anywhere. So I put more time into the program. However, some people not doing like exactly what I'm doing. Okay, so anyway, we keep running. So far, so good. And Mr. Smith can see the problem, right? Before we don't have anything, now we get everything.
No, I understand what you're saying, Mr. Pham. If something goes down, they don't really have like a service or somebody to make the repairs and do the necessary things to keep the system going. That's what you're essentially saying. If something breaks down, they want you teachers to do all the fixing and the repairing. They're not going to hire or contract out somebody to do it.
Yeah, that is right.
Well, they got to
Oh.
take your class to understand it.
The thing is they want to spend less money. That's why they
Everything's
say,
about money.
that's why they say if the less than 25 students for one class, they cancel. The thing is they pay for more, but they get back it less. They don't want to do that way.
Everything's about the almighty dollar. Okay, well, thank you, Mr. Pham.
Yeah, no problem. You know, I went to get a few days off. That's good. Okay, and we'll see you on Monday.
Okay, see you all next week.
Yeah.
Thank you
Bye-bye.
very much.
We'll call you soon, Sam.
Thank
Okay.
you. Goodbye.
I'm on vacation.